And I'm going to turn on my camera. Okay. So when we left off last class, we were starting to talk about, we had just finished talking about rotations of single bonds in linear alkanes. And we decided to call it quits before we started talking about cycloalkanes. So cycloalkanes are exactly what it says they are. They are alkanes in cycles. And if we note, now we have the molecular formula CnH2n, because we've had to remove kind of one hydrogen on this carbon, one hydrogen on that carbon, and attach them together to make a carbon-carbon bond. So we lose a equivalent of hydrogen gas to turn a linear alkane into a cycloalkane with the same number of carbons in it. So, yes, I'm used to having my, there we go, mouse being able to go between, but now I'm on the university internet and that stops me from doing things like that because that would be convenient and we can't possibly have convenience. And that's going, there we go. So in terms of physical properties, they're like really, really compact branched alkanes. So they're normally, because they normally have even smaller surface areas than most even branched alkanes because they can fold back in on themselves because they are cyclic. So you have everything you expect from that. They pack really well, which means you have higher melting points than you expect for something of a similar size. And they boil really easily because they have very low surface areas, so they have fewer opportunities for London dispersion interactions. And so they boil at a lower temperature than you would expect based on alkane of a similar size. So here are some values. They're all about the same, as you can see. The densities slowly increase as you increase the size. And your melting points go up. You have a weird little bump here between the even and the odd ones, which is what we've seen. And then you have a steady increase in boiling point because you have a steady increase in the surface area. But they're still smaller than you would expect for a linear equivalent. Again, don't really care too much about this. Naming them, I'm sure you've named these before. Use the base name and then you add cyclo to it. So this is a cyclopentane, this is a cycloheptane, this is a cyclohexane. And if there's only one substituent on it, you don't need any numbering because, of course, your one position is the place where the substituent is. If you do have multiple substituents, you do need numbering. So when you're going through this thing, you want to give yourself the lowest possible numbers. And then, again, just like everything else, order alphabetically and name alphabetically. So there's an ethyl, there's a methyl. The ethyl is the priority group. It's higher. They're both equally important. They're both alkyl chains. Ethyl is higher alphabetically, and so you're going to try and privilege that with the 1. And you're going to go 1, 2 instead of 1, 2. Because if you did 1, 2, 3, 4, then your methyl group would be named number 4, and that wouldn't be very good. So you want to go the other way. We see the same thing over here, where we've got 2 methyl groups on 1, so obviously we want to give that priority, that position over the other position. And over here, we're down to that issue with, again, 2 ethyl groups on 1, so we want to give that priority. Oops. No, I don't want to mark things. I want to go to the next slide. Okay. If your cycloalkyl group is a smaller component of the chain, then you name it as a substituent. And again, this is just a reminder for that. So this is one place where we are going to talk about cis-trans. So we've talked about with double bonds, and now we're going to talk about the rings, and we're going to use this as a convenience. This is not an official naming thing, but it's going to matter a lot when we're talking about reactions. And so it's a good idea to get a sense of spatial arrangement of atoms. So you can have cis and trans. So if you have a molecule like this guy here, the two methyl groups are both below the plane of the cyclohexane, pentane, cyclopentane. It's been a really long Monday. And so these two groups are both down below. They're on the same side of the cyclopentane. So they're cis. This is the same molecule, except the spatial arrangement has been changed. These are stereoisomers. We're going to come back to that term next class, or maybe even later this class, if I can move quickly enough. And so what we have here is all the attachments are the same. Everything's attached to the same thing. It's just arranged differently in space. And in this case, the two methyl groups are on opposite sides of the plane formed by the cyclopentane. And so it's a trans isomer. Okay. Oops, I do not want subtitles. There we go. If you want practice doing these kinds of problems, there's quite a few. This builds into ones for next lecture as well. But there's a lot of practice drawing these things and playing with these things. So we talked a bit about alkanes. We talked a bit about the importance of rotation here. And we introduced the idea of cycloalkanes. Now, attached to the end of this slide, I have some notes on how to go about naming alkanes if you do need a review. I'm not going to go through them today, but they're attached to the end of this lecture for you if you do need to review that and you want to see it from a different source. Though I have a feeling like a lot of online sources and textbooks might be a bit more detailed and a bit more useful. Oops, that's not particularly useful. So now we're going to talk, I think some of this is now going to start moving into new things for almost everybody starting this class. So we're going to talk about conformations of simple rings and some simple systems like these. So we want to talk about angle strain and torsional strain and define what those are and how they both go into ring strain. We're going to draw some cyclohexanes and talk about the conformational preferences of cyclohexanes. And that's basically what we're going to cover. Then we're going to talk about bicyclic systems. But the huge chunk of this thing is going to be on point 2 here because it's pretty important. So if we want to talk about strain is energy that is required to overcome non-ideal situations. And so we've just spent a lot of time talking about sp3 carbons. They like being 109.5 degrees. So whenever a bond angle cannot be 109.5 degrees, there is strain. And we call that angle strain because the angle wants to be 109.5 degrees and it's not. And so things are being either pushed open or pulled closed away from this ideal. And so electrons, one way or another, are closer to one another than they want to be. And you pay a cost within the same atom, and you pay a cost for that. Those atomic orbitals, those linear combinations of atomic orbitals we've been drawing, those sp3 orbitals want to be 109.5. And if you start making them closer or further, you start putting stress on the rest of the system and bumping them into each other. And so the reason why 5 and 6 membered rings are so favored over every other size of ring is because the bond angle can be almost exactly 109.5. In 6 membered rings, it is 109.5. In 5, it's a little bit smaller than that, but it's like 108.7 or something. It's essentially the same thing. The second type of strain that we're going to see is torsional strain. And so this is what happens when the angles involved and the shape of the ring doesn't allow for things to be eclipsed. Sorry, staggered. Stuff wants to be staggered. Stuff wants to be anti-staggered. We talked about this last class. In a free chain, like a linear alkane, there's no reason you can't everything be anti-staggered. It can access that at that state. Whereas in a cyclic system, it can be such that you just don't have that flexibility to move. You can't just spin everything. So, I've got my handy model kit here. I had a 5-member ring, but I want to make it into a 4-membered ring. So first of all, my model kit is very unhappy as a 4-membered ring. If you bought one of these and you've been playing with it, they like making 5 and 6s, and that's because all these plastic pieces are designed to make 109.5 degree bond angles. And when you make them 90 degrees like I have here, it's not a happy camper. So this is angle strain. You can actually, angle strain. You can actually see it in the model. The model is unhappy. For the torsional strain, you can do is you can look down that bond, and what you can see there is you have this red atom in the front, you have this black atom in the back, hopefully, and those pieces here, whatever's here, hydrogen atoms would be it because there's nothing labeled on them. Those are too close to each other. Those are eclipsing each other. And unlike in a free linear chain, I can wiggle it a bit and try and sort of break them up so you have a slight difference in bond angle, but it's not much. They really almost want to be eclipsed. They don't really have much freedom here. And so this is torsional strain. It's because the substituents, the atoms attached to this carbon and the atoms attached to this carbon, they're in line with each other and they're eclipsing each other. And that's unfavorable. So that's the torsional strain we're talking about here. And I was doing that with my camera, so if you weren't paying attention to the camera, it didn't make a lot of sense. I'll try and say when I'm switching over to the camera, because I'll be doing that again later this lecture. So together, these things combine to form ring strain. And so what we can note is that, well, what you should see is whenever you burn a hydrocarbon, there's a pretty simple math to how much energy is produced. You put carbon and hydrogen in, you add oxygen, you get water and carbon dioxide out, plus a certain amount of energy. And we can sort of measure the amount of energy, and then we can divide it to get the amount of energy per CH2 atom. So theoretically, if you divide by the amount of energy per CH2 atom, if there was no strain or anything, there's twice as many CH2s in a cyclohexane as in a cyclopropane. And so you expect one molecule of cyclohexane to release twice as much energy as a molecule of cyclopropane. Or one molecule of cyclohexane to release the same amount of energy as 2 molecules of cyclopropane. Because you've got 6 CH2s and 6 CH2s. But that's not what happens. You get different amounts of energy depending on what the ring is. And that's actually what you're actually measuring, is you're actually measuring a ring strain. Because you're measuring how much more energy is released when you burn this thing up and you get rid of that ring strain. And so cyclohexane is basically our 0 marker there. It's the lowest energy thing. And if you'll notice, if you go higher or lower in ring size, there's ring strain. So a 5-membered ring is more strained than a 6. A 7 is more strained than a 6. 6 is just perfect for the angles. And at the very bottom there, you can see it says a long chain alkane, and it has the values for that, and it's exactly the same as a 6-membered ring. So we have quite a big jump going from a 4-membered ring, 5-membered ring to a 4-membered ring, 27 to 110, and it's a much more moderate rise as you get bigger. And it kind of maxes out at about 9 and starts falling off again at 10 and above. We don't worry too much about that. We're really only going to be worrying about the guys that are on this page. So 5 and 6-membered rings are awesome. They're easy to form. They're low energy. There's no angle strain. There's limited torsional strain. 3 and 4 are really bad. You can see I'm not even going to try and make a 3-membered ring model with my thing. I will break it. I actually have special flexible ones that I can use there's super flexible versions that I can go ahead and do that with, but I just didn't get enough of them here together right now. So if we start looking at these things in a bit of detail, you can sort of see why this is so bad. So the cyclopropane, first of all, it's a triangle, and you got three things, and they got to be in a plane, because if you have 3 points, you can put 3 points in a plane always. So they are, and so you have a perfect 60-degree angle between each of these. That's bad. It wants to be 109.5, and it's 60. 60 is a lot smaller. So that's a pretty unhappy molecule. And you can see it in what sort of happens here is that the orbitals distort a little bit, but they can't completely. And so what you do is you end up getting these weak sigma bonds, because you don't have that good overlap you expect to see between the two atoms. You really expect all that electron density to be directly between the atoms, and it's not. It's kind of off to the side. Now they've kind of exaggerated this for effect, but it's off to the side. And so that bond's not very strong. So it's already going to be easier to break that bond. And we have this other problem that all the bonds are eclipsed. Because whenever you have this, the problem, you can sort of see it here. You're looking down any one of these carbon bonds. Your hydrogens are going to be trying to overlap each other. And they're stuck like that. They cannot get out of that. So we have really sucky angle strain, and we have really sucky torsional strain, and so we have really sucky total ring strain. Cyclobutane is slightly better, because as we were looking at it there, we were able to play with it and twist it. If you want to see that again, I like playing with models. Like we had this, now I've got it perfectly in a plane, but I can distort it a bit from the plane. I don't know if we can see that. It's a little bit puckered. And it's going to pucker itself a little bit like it's saying there. You can sort of, I'm trying to reproduce the picture here. It's a little bit, it's not flat. And the reason is if you look down any of those bonds, we're slowly trying to get it slightly out of eclipsed by doing that, by puckering it. And that's why it puckers. That's actually, that bond angle is not very good. That one's basically completely eclipsed. It's pretty minor. It's one of these skew things you're saying. It's in between eclipsed and staggered. But it's better than the cyclopropane, which is stuck in a plane. Cyclopentane, for the first time, we get to relax it, and my model actually wants to build a cyclopentane. It's pretty happy with that. So I know there's not a lot of angle strain because it's not trying to break these little pieces of plastic. And again, if it's completely flat, what you'll find if you try and build a completely flat cyclopentane, it won't actually be all that happy. That's what I've done here. It's completely flat. The bond angles release a lot better when I pucker one of the atoms down. So keep 4 of them flat in a plane, and I pucker one up or down. This is called the envelope conformation because it kind of looks like an open envelope. Like, I don't know if you have an envelope and you open a tab a little bit. It doesn't look like an envelope at all, but we still call it that. And when we do that, if we start looking down these bonds, we start seeing that, oh, that looks pretty good. That actually looks pretty staggered. And we can do that for all of them. We can just walk along the bonds. If you're not following, I'm kind of trying to line them up in my camera. And they vary depending on where they are relative to the puckered atom. Oh, look, that one's pretty much eclipsed. That one should also be pretty much eclipsed. And then we're going back to decent staggering. And it makes sense at the back too, away from the puckering are eclipsed because they're in the plane. They're kind of locked in the plane. But this is still the best we can do with this. And so we do have some ring strain because of this eclipsing interaction at the back here. But we've gotten rid of a lot of the angle strain. So we have torsional strain, but not much angle strain. And finally, if we switch to a 6-membered ring, we get rid of everything that is bad in this world. So there are many if you ever build one of these things, they're pretty floppy now. For the first time, we actually kind of have something I can bend and do all sorts of things with. Um, for the first thing you notice is it really wants to make six-membered rings. Your model kit will love you for it. All the bond angles are 109.5 degrees, so it's incredibly comfortable. And now, if I walk down each of the bonds, if I had done this right and my kit hadn't been a little bit disrupted by being beaten up, all the bond angles are basically perfectly staggered. Everything is perfectly staggered. And so we don't have any angle strain and we don't have any torsional strain because everything is perfect. This is called a chair conformation. It's called a chair because here's the flat piece of the chair. There's 4 atoms in the middle. It's like a lazy boy. There's a back to the chair, and then there's a leg piece to the chair. I don't know, leg rest. It's kind of in the down position. So the whole thing is kind of like a flat base of the chair with a back and a bottom. And we draw it the way it's drawn there on the board. And so I think the next slide I think is about. Oh, there's a question. Yeah, this is peak ring performance. The chair is perfect. There's another conformation we do talk about called the boat conformation, where I take the footrest and I flip it up. Now it's in a boat. It looks like a boat because there's a bow and there's a stern, or a bow and a stern, depending if you like left to right or right to left. And then there's a flat paw of the boat. Like the boat has a big hole in it, so it's not a very good boat. But this is considered, it's called the boat conformation. This often gets taught when this is often taught, it's like, hey, it's a stable conformation of a 6-member ring. It is not a stable conformation of a 6-member ring. This one sucks. And it's because the atom here and the atom here kind of too close together and they're banging into each other. We also now have eclipses on both of the sides of the boat. And if my model kit wasn't bent, these would be perfectly eclipsed. So we've now introduced torsional strain. And we have this weird ass steric strain in here, which is a complete self goal on oneself. Like this was completely unnecessary. So a boat conformation is an unstable conformation. So things don't actually exist as boats. They exist as what's called a twist boat, where they twist a little bit out of the boat conformation. And now actually things get more eclipsed and we break things get more staggered. You can see there that was eclipsed in a boat, and now it's kind of skewed. It's kind of skewed. That's actually pretty good. And you can walk around this. And all I've done is I've kind of broken my boat up a little bit. I pushed one of the other atoms down. So instead of having a nice plane here, now I have a plane here, and this one is kind of going down in a little weird way. And that's called a twist boat. And that's basically how these things exist. Sometimes these also got called, they're very similar to twist chairs. But a twist chair generally has 4 of the atoms, the back 4 in this case, all on a plane, and then the one atom here in front is above, the black atom here is below. That one's called a twist chair, and the other one is a boat that's a little twist, is a twist boat. I don't care too much about that. That's the reason I'm kind of glancing over this thing. We're really going to be worrying about chair conformations for this course. But all these things exist, and you can kind of play around with your 6-membered ring and make it wiggle. Yeah, everything is less stable than a chair. Chair is the moat. Claire asked, is a twist boat still less stable than a chair? Everything is less stable than a chair. So we get this kind of graph if we show like small changes in bond angles. So what's happening here is the chair goes through a half chair where we get more eclipsing conformations, really bad, a whole bunch, because 6 and 1, 1 and 2, all these ones all completely eclipse each other. You got this kind of thing where you have this kind of thing sticking up and it's kind of in the way. That can fall down to that twist boat, which I was showing, which is a sort of a local minimum. And then we have another local maximum, which is the boat, and a local minimum for the twist chair. and then up to the half chair again, and then all the way back down to the chair. So these energy differences are 10 kilocalories per mole. There's enough energy at room temperature for these chairs to flip back and forwards quite readily. So these things do interconvert. Okay. So now, let's say I attached a blue atom, it's because it's blue, to my thingy, my chair. So you always have, you think, God, there are a lot of atoms here. There's got to be a whole bunch of different chair conformations, but there's not. There's actually only two. So what we have here is I've got these four atoms clearly in a plane. That looks like a plane to me. That's a square. But it's kind of arbitrary that I picked those four atoms. Because, wait for it, so we've got these two red ones, these two black ones. Now I'm going to switch. If I go with these two black ones and these two red ones, or these two black ones and this red one, black one, we're now still in a chair. I haven't bent any bonds, I haven't done anything, I haven't rotated any bonds. All I've done is rotate the entire molecule, and I found a new plane. And so there's three planes with four atom planes in this chair. So for any given six-membered ring, there are two chairs. And so one way to do this is to look at, okay, well, I've got this molecule, and I'm going to draw it on, and you guys are going to see something different than me. Shit. I'm just going to orient where the red ones and blue, where R represents red and B is the blue substituent. So I have this chair, and then to flip to the other chair, to change to the other chair that can be happening, I have to go through the boat. So there I went through the half chair. When it's really hard to get into the half chair, like that's the half chair. It doesn't want to be there. I do anything and it twists its way out, and that's because you can actually feel the angle strain in your molecule. If I touch this at all, it twists. So I go through the boat, then I flip the other end up. So what I've done is I've kind of the carbon that was above the plane has dropped below. The carbon that was below the plane has gone above, and I flipped the chair. And so what that is, I'm going to try and hold this thing up to the screen while I'm doing this. We've got the red, and then we have the blue that's up. So those are different because the blue is in a different place. In one of them, it was in this, we call this equatorial. This is the original chair. And you can see why maybe it's called equatorial when you think about the chair, because, hey, look, it's on the equator. It's in the plane of the chair. And then we call the other one axial because it is vertical. It is in the axis of the chair. So this is axial. And that says axial, not axid. And this is equatorial. So we have these two different forms. Yeah, so the high melting point and boiling point, Babian asked, so how melting point and boiling point reflects the stability of the cyclohexane chair. No, it doesn't. It's got fuck all to do with that. The high melting point and boiling point, the high melting point of this is because the molecule's gotten bigger. They pack nicely together. But if you start increasing the size of it, you'll increase the melting point. So a cycloheptane is less stable than a cyclohexane, but still has a higher melting point. Or a cycloalkane definitely does. And the boiling point increases, you add extra carbons because you increase the surface area. So it's a function of surface area for the boiling point. It's a function of packing ability for the melting point. It's got nothing to do with the stability of the chair. The stability of the chair means that you have a low heat of combustion. You don't get as much energy out of a cyclohexane as you do out of a cyclopropane. Well, two cyclopropanes. Because there's this extra energy in the cyclopropane bonds because they're unstable. So to keep those things bound together, you need extra energy in there. No, they're not. So the equatorial and axial are not equally stable. And why is that? Well, let's just look at, I'm going to grab another atom. I got some atoms in a drawer over here. It's kind of like Mr. Dressup's tickle trunk, except it's nowhere near as fun because it's atoms. Okay. So I'm going to add another substituent to this guy. And what I'm going to do is I'm going to make this really clear by kind of double. Okay, so what I've done, if you look at the camera, is I've got my 6-membered ring, and I have 2 thingies attached to it. And right now they're both axial, and so they're both ethyl groups, let's say. That's not good. Whacking things together is unstable because that means all those electron clouds are just such a kind of fun, are banging together. This is bad. And it's really, really clear when I've got big things here. But even if those guys aren't there, these electron clouds from these 2 guys are close together and whacking into each other. And even if this guy's not here, this guy's electron clouds are a little bit too close to the hydrogen here and the hydrogen that's on here. So the axial guy is interacting with the axial guy that's 2 carbons over. And it's because they're kind of close together. Now, take that same molecule and I flip the chair. So I'll make sure I had this in. So this was the chair. You can see the 1, 2, 3, 4 atoms in a plane. This guy's up. I'm going to pull that one down, and I'm going to pull that one up. So I flipped the chair. And now what we can see is that these 2 things are nowhere near each other. They're waving around in the middle of freaking nowhere. And so they're not whacking into anything anymore. They're nice and far away from all the other atoms. So axial equals bad. Steric interactions. So all those interactions we were talking about are occurring in the axial. So we can actually see them. So here we're going to look at the equatorial ones. I want you to look down that bond. It's actually a little bit difficult. You know what? It's almost like I'm looking down these 2 bonds, like skipping around this carbon. So we got a hydrogen up here, a hydrogen up here. This is called a 1,3 diaxial interaction. 1, 2, 3. So 3, 1, and 3. Diaxial because that's axial and that's axial. And these 2 are interacting because they exist. Right now they're hydrogens. It's the smallest thing they possibly can be. So this is considered to be the 0 state. But as soon as I put these guys here, now we've got this big freaking thingy and this big freaking thingy, and they're both big and they're both whacking into each other. We have a bad 1,3 diaxial interaction. This is why 1,3 diaxial interactions get a bad rap. It's because they're bad and things whack into each other because of steric strain. Sterics is really electron on electron violence because they're getting a little bit too close together. Yep. Axial is always worse. So you are going to need to draw a lot of chairs. So you can learn how to do this the way you want. one way that works is you draw two parallel lines, roughly parallel lines, offset a little bit. Then we draw two more parallel lines. And then we close the chair. And so what I've got here are three sets of parallel lines, and I'll highlight that in my next drawing. Set number one, set number two, set number zoom in, set number three. Is anyone red-green colorblind in this course? Okay. I will try and avoid using red and green, Grayson. Sorry. When I'm trying to highlight that. So I'm gonna switch out of red and green for that because I do have red and green. Just use black. Shit, black is really close to blue. Okay. I will change the blue to a lighter blue. So we've got three sets of lines there. We got black ones, we got blue ones, we got red ones. I have trouble drawing it this way, but we have so when I don't screw up my drawing, I kind of draw it all kind of at once. The important thing is that you've got roughly three sets of parallel lines. Pick what works for you. What we should have now is every single atom has an axial. So, and they change over. So, if I take a look at this baby, the axial for this carbon, the vertical one is the axial one, it's up. And the next two carbons over, it's down. And we can see that in our drawing. Note that I kind of indicated that the one bond kind of goes in behind it by kind of breaking the line. And so these two are both down. The next two next to them must be up. And then this final one down here that I was holding on to is down. And so we have this down, up, all the way around. Every atom, it switches from being down to being up. And that's just the nature of tetrahedra arranged in a six-membered ring. And that's not what I intended to do. Still not what I intended to do. What did I do now? I'm really nervous to press buttons now. Okay. And then everyone has an equatorial. Now the equatorials are drawn kind of to finish the tetrahedron. And what we'll notice here is that I actually should do better on this. The equatorials should be parallel. You know what? I'll actually do it on this bottom guy over here. It's going to be clearer. No. Ugh. Okay, I obviously pressed the wrong button at some point. My equatorials are going to be parallel to the one set of parallel lines that is not on that carbon. So this carbon is attached to the blue and red parallel lines. So it's equatorial carbons or equatorial bonds. They're just hydrogens in this case. So I guess if I'm not putting anything on the end of them, they're all carbons. So I'll put some hydrogens on the end. Should be parallel to the third set of parallel lines, the ones that do not make a bond with that carbon. And that's the black ones, and those are just absolutely planar. I think I'm clicking too fast, but with the pen. So this carbon here is not attached to any of the blue ones, so its equatorial should be parallel to the blue lines. And same thing there. Going back away into the page. And this guy is not parallel to the red ones. And so its equatorial should be parallel to the red. It's not quite parallel, is it? And so, when you've done this, right, when you only have 4 sets of parallel lines, you've got the 3 sets that make up the ring, plus the equatorials that go with them. And then you have the axials, which are all parallel one with another because they're all vertical. I like drawing these off at an angle whenever. Now, of course, I'm really self-conscious because I am drawing them in front of a class. I don't quite draw these 2 lines here horizontal. And the reason I do that is because then it looks better when the axials are axial. And what's important here, ideally when you're drawing these, make your axials vertical. Because what makes it really hard is if I ask you to draw an axial bond, and what you draw is that. I don't know if that's axial or equatorial. And because I don't know if it's axial or equatorial, you get a 0. So it's really good when your axials are axial and your equatorials are more or less in the plane. Yeah, so on this red one, the equatorials are on that slide somewhere. No, I said I wasn't going to do red, green. Bad, Dr. Trans. Okay, blue. The ones on these ends, no, I don't want to do whatever you told me you want me to do, are kind of easy. I think those are always the easiest ones to draw because they fit. Those are equatorial. The blue ones are equatorial. Blue is equatorial. Because they are, I don't know, like I can't explain why that seems like the only place you can possibly put that bond. It finishes the tetrahedron. I find the ones on the other 4 carbons are a lot more complicated. This guy's not bad. And again, what we're looking at here is roughly this bond here should be parallel to the bond in the ring that is now attached to that carbon, which of course is this guy here. Those are roughly parallel. This one should be roughly parallel with that too. Notice that these equatorials aren't quite horizontal. They're a little bit off the horizontal. And I'm going to come back to this in a second. This guy wants to be equatorial with this bond here. Or parallel, and that one does too. And so those are where my equatorials are. And what's important here is that on every single one of the carbons, you clearly have an up bond that is above the plane of the cyclohexane and a down bond which is below the plane of the cyclohexane. The number 5 is my way of trying to say this in words, that the equatorial should be parallel to the one that is not part of the one bonding to that carbon. It is really difficult to argue that or to phrase that in English. Geometrically, it's a very simple argument. And I'm trying to change the slide, but instead I am writing in blue ink. There we go. So when we have a substituent cyclohexane, we're working towards this already. Your substituent can flip between being axial or being equatorial if there's one substituent. And these are drawn such that the equilibrium, first of all, these aren't equilibrium arrows. They're double-headed. So in equilibrium, we're showing we have a single head, and it should direct where that's going. And so we have this equilibrium between these things. The chairs are favored over the boats. But then if we're going to compare the two chairs together, the overall equilibrium lies towards having that methyl group, the CH3 group, equatorial, because it's not whacking into all those little hydrogens that are axial as well. The axials are whacking into other axials, and that's not good. So the equatorial is more stable than the axial. And note that the hydrogen here is equatorial, the hydrogen here is axial, but the CH3 is bigger. And so that's all that matters. Which one is bigger? Because you want to get the big thing equatorial, because then its big thing's got more electrons taking up more space. And so you want those away from everything else. And so axial conformation basically has two gauche interactions that you don't have in equatorial, and that's why it raises the energy. Whereas in equatorial position, so we can see this with this guy, I've got a chair, and I'm looking at that, and that's axial. You got a gauche interaction with this bond here, and you have a gauche interaction with this bond here. But if I make this equatorial, now I'm anti with the big carbon bond there. And I'm anti with the carbon bond on the other carbon next to it. So I'm anti on both of the carbons that carbon's attached to, whereas if it was axial, I'm gauche with this one, and I am gauche with this one. And of course, the gauches are worse than the antis. What we're really worrying about, again, is this guy here bumping into these two hydrogens because whacking. And that's why these are called 1,3 diaxial interactions. Now, the bigger the substituent, the more it favors being equatorial, because the more opportunity it has to whack into things. That makes perfect sense. So fluorine is the smallest atom after hydrogen. The difference in the energies of the axial minus the equatorial is almost, it depends if you like kilojoules or kcal. I'm good either way. Let's take a look. We'll just go through the kilojoule column. This is just a unit conversion. So fluoride's the smallest thing. It's got a small energy. It prefers equatorial, of course, because it's bigger than hydrogen, but it's not that much bigger, so it's not a humongous preference. Cyanide, it's got two atoms. That seems like it must be big, but what we have to remember is cyanide is very linear. That nitrogen carbon is making a triple bond, so all those electrons on that carbon are kind of tucked in away from everything. And so all we're seeing is like a carbon without its splay of sp3 orbitals all around it, which really make the methyl group big. The cyanide is nice and got them all tucked away into an sp orbital. That's directly opposite all of this. So although, yeah, carbon's bigger than fluorine, and the nitrogen carbon is definitely bigger than fluorine, close to the chair, it's not that much bigger. So we get basically exactly the same energy. Then we start going for bigger atoms. So we go to a chlorine, still single atom. It's bigger than fluorine. Now we start seeing a size difference. Go to something bigger, see a size difference. Go to an OH where the H is in an sp3 orbital. So unlike the CN, which was sp, the H is an sp3 that's bent down towards. Now you got all the electrons of the oxygen, and then you got these sp3 orbitals and these lone pairs, and there's size and everything. There's an extra atom, and you're looking at something considerably bigger. You take a carbon, you dump a bunch of oxygens on it, make one of them double bonded, so it's pretty close into the carbon. Now there's a lot of electrons pretty close to that chair. That's much bigger. but at least they're 120 degrees and they're flat and they can rotate a little bit out of the way and you can start playing with that. CH3, you're stuck with a tetrahedron. Bad news, bigger. Now you start replacing the hydrogens with a carbon, it gets bigger. You replace 2 of the hydrogens with the carbon, it gets bigger. You replace 3 of the hydrogens with the carbon and you're screwed, and it gets a whole lot bigger. And the way we can think about that is, let's just see that, why there's this humongous jump from methyl to ethyl. So let's say you had just methyl. That's this guy here. This is an ethyl group up there. It's a CH2CH3. You know, it's axial. It's bad. I get it. But I can tuck this extra carbon out of the way from the ring. So it's not whacking into these hydrogens. So yeah, it's a little bit bigger than a methyl, but it's not that bad. I go up to the isopropyl, which is the 8.81. Okay, now I got 2 of these. I don't want either of these guys near anything over here, but I can deal with that. I can bend it like this. That's okay. I might not have like free. It's not quite as happy to spin around as you'd want it to be, because spinning is fun. Bonds like spinning, and we're not going to be able to spin as easily because we have this conflict. But you know, I can still have a small hydrogen over here, which is as small as I can get. Jumping up to the tert-butyl. Okay, now I'm in trouble. Like, no matter how I orient this, I've got some of these bang into those, and there's no way around it. And that's why you see this humongous jump from 8.8 to 23. And I think it is 220, so I think we're going to leave it there. And next class, we're going to talk about some disubstituted cyclohexanes, and then we're going to be moving into a discussion of stereoisomers. If you haven't gotten out your model kits, now is a really good time to get out your model kits. And actually, I'd have them ready for us to talk about stereoisomers next class. So if you've got one of these, get it out, it'll help. If you don't have one of these, get out some marshmallows and toothpicks. Get some food coloring on them and color them different colors. That can kind of work, but this is probably better. Okay. Actually, you know what? This works a lot. This is actually one of the things where rare occasions where this actually works better over Zoom than in person, because I can like put the model kit right up to the camera, and I can make sure you're seeing what I want you to see. In person, it's not as easy to do that. But this is, of course, going to have been video recorded, and so if you want to sort of play along with this later, that's, you know, you've got this video. Okay, thank you very much.